Good afternoon, everyone. Welcome to the second day of lecture series on IoT and its application. Myself, Prema NS, working as Associate Professor, Department of Information Science and Engineering, VVC Mysuru. Today we have with us Dr. S. Meenakshi Sundaram, working as Professor and Head, Department of Computer Science and Engineering, GSSS Institute of Engineering and Technology for Women, Mysuru. He will be talking about smart object and connectivity. From the Department of ISE and VBCA, I welcome him. Over to you, sir. Thank you.
Thank you, madam. Thank you. So in today's online lecture series, so we will study about the smart objects, the things in Internet of Things. As we know, Internet of Things has become popular in the recent 1 decade only, maybe after 2010 onwards. We are able to see the impact of Internet of Things everywhere. So actually going into the topics, first we will see about the sensors, actuators, smart objects, and various protocols related to Internet of Things. First we will see about the things in Internet of Things. We will see about the sensors, actuators, and smart objects. So which includes the capabilities of the sensors, actuators, and smart objects, the characteristics and the functionality of all these. So as we know, sensors, a sensor normally senses, where more specifically a sensor measures some physical quantity and converts that measurement reading into a digital representation. So the device which is capable of measuring or converting into measurements and storing it in a digital form, we call it as a sensor. So the digital representation is typically passed to another device for transformation into useful data that can be consumed by intelligent devices or human beings. Actually, with only these measurements, there is no validity. So if you want to further put this data into use, we have to process the data and we have to extract some useful information. So that should be made available to human beings or to some other device for understanding these data values and using it for some other applications. So sensors provide some superhuman sensory capabilities. Sensors can be readily embedded into any physical objects that can be connected via internet, maybe wired or wireless. Now we will try to classify the various types of sensors. So we can classify into 6 categories. The first category is we can call it as active or passive sensors. The second one is the invasive or non-invasive sensors. Similarly, the contact or no contact sensors, absolute or relative sensors based on the area of special application and how sensors measure or what sensors measure. Like this, we can have 7 categories and we can understand about the characteristics and properties of sensors. First category we will take as the active or passive sensors. See, some sensors are capable of producing energy output and typically require an external power supply. We call it as active sensor. See, wherever we have sensors which simply receive energy and typically require no external power supply, we call it as just passive sensors. So the passive sensors require no external power supply. Similarly, if we take the second case, the invasive or non-invasive sensors, so sensor can be a part of the environment in which it is measuring some sort of data. So we call it as invasive, or external to the environment, we call it as a non-invasive type of sensor. Similarly, contact and no contact sensors. Sensors can be categorized whether they require physical contact with what they are measuring, with contact or without any contact. So the physical contacts made or no contacts made categorizes these types of sensors. Similarly, we have the absolute or relative sensors. Sensors are categorized based on whether they measure an absolute scale or relative with reference to some fixed or variable values. Okay, that reference when it is made as a mark and relatively vary, then we call it as a relative sensor. Similarly, based on the area of application, sensors can be categorized based on the specific industry or vertical where they are being actually used. So it depends on the industry or the verticals where we are actually going to use or apply these sensors. Based on that, we can categorize the sensors, and based on what they measure. See, for example, the inputs what sensors can measure, for example, maybe thermoelectric or electromechanical or piezoresistive, optic, electric, or fluid mechanic, or photoelastic. Like this, whatever maybe the sensory inputs these devices take inside. Based on that, we can categorize the sensors and what actually they measure. Okay, so sensors can be categorized based on their applications or what physical variables actually they measure, the varieties of physical variables what they measure. Based on that also we can categorize these sensors. So the categorization, we can see position sensor. So where we can use it for positioning sensors, position an object, or we can include absolute terms, relative terms for displacement, or identifying the position. For example, whether it is linear, angular, or multi-axis. So like that, it is a position sensor. Examples are potentiometer, inclinometer, or proximity sensors, where we are able to understand the closeness of the objects. Similarly, occupancy or motion. Okay, so we are able to understand, for example, you take a surveillance area, we can understand the motion of people, and we can detect movements of objects or people, and we are able to understand whether items are stationary or mobile. Examples we can call as the LI radar. Similarly, velocity and acceleration. So velocity for identifying the speed of the motion. It may be linear or angular, or indicating how fast an object moves, whether it is in a straight line, or how quickly it rotates, or how the acceleration sensors measure the changes in velocity, like as we do in an accelerometer or a gyroscope. Similarly, force sensors, pressure sensors, and flow sensors, where we can understand the force, physical force applied, or whether we can understand the magnitude of the force, whether it is within a limit or beyond the limits. For example, if we take a force gauge or a viscometer or a tactile sensor, a touch sensor, we can understand the force with which we are able to touch the objects or understand the proximity. Okay. Similarly, the pressure sensors, for example, if you want to apply it for the liquids or gases, we can understand the pressure in terms of some unit area. For example, if you take the barometer to understand the pressure, or a Borden gauge or a piezometer. Similarly, the flow, the rate of flow, the mass or the velocity. So we can measure such quantities. So for example, anemometer or the mass flow sensor or a water meter. Similarly, acoustic for measuring the sound levels and how we actually convert the information into digital or analog digital signals using microphone or hydrophone, etc. Similarly, humidity for understanding the amount of water vapor present in the air or in the mass. Okay, humidity levels can be measured in various ways, as absolute humidity or relative humidity, mass ratio, and so on. We can use hygrometer, humister, soil, or moisture sensors. Similarly, light sensors for understanding the presence of light, whether it is visible or invisible. Like as we know, infrared sensors or photodetectors, flame detectors, wherein we can sense the light, the intensity of light, presence of light, or no presence of light. So these are some of the sensor types. And one more is the radiation sensor type, where we can understand the radiation in an environment caused by scintillation or ionization reduction. Example, if we take a scintillator or a neutron detector, we can understand the amount of radiation that has taken place or takes place in a device. Similarly, to understand the temperature sensors, we can understand whether the objects it's very hot or cold or warm, or whether we can measure it using contacts or no contacts. And no contact sensors do not need any physical contact. They can measure the temperature through convection and radiation. For example, if we take thermometers, calorimeters, temperature gauges, etc., where we are able to measure the temperature with or without contacts. Similarly, chemical sensors. So wherever human beings are not able to go and capture the actual data. For example, chemical reactors. For example, chemical centers measure the concentration of chemicals in a system. When we mix it with chemicals, these sensors can target the levels. And for example, a breath analyzer or a olfactometer or a smoke detector, we can understand the levels which can be measured. Similarly, biosensors for biological elements such as organisms, tissues, cells, enzymes, antibodies, nucleic acid, etc., where we are able to understand the levels of blood glucose or biosensors, pulse or ECG. We are able to understand the actual readings. For example, let us take one practical example of a precision agriculture or a smart farming, wherein we want to improve the efficiency, sustainability, and profitability of the traditional farming practices. And this has also proven successful, where we use sensors, power of sensors. We are able to understand the extent which the sensors are capable of helping the farmers in agricultural area in precision farming. And this includes, we are nowadays comfortable with GPS and satellite aerial imagery for determining the field viability. For high precision, we can use robots for planting, harvesting, irrigation, and so on. And real-time analytics with artificial intelligence, recently, we are able to embed with IoT, and we are able to use these AI techniques to implement or predict optimal crop yield, weather impacts, soil quality measurements. So we are able to understand and come to quick conclusions based on the data, whatever is sensed by these sensors. And more significant impacts on the sensor in precision agriculture are dealing with a variety of soil characteristics, wherein we are able to understand the quality of the soil, the pH levels of the soil, the salinity, the toxic levels, moisture levels for irrigation. We can plan for the irrigation, then nutrient levels for fertilization. And we are able to make quick planning based on the data collected with these sensors. And this North Dakota State University, they have developed one kind of sensor, which is called a biodegradable sensor, which can be used to understand the, see this one example of the biodegradable sensor developed by North Dakota State University for smart farming. So this figure shows the biodegradable passive micro sensors to measure the soil and crop and the relevant conditions in the field. Now coming to the impact of the smartphones. The smartphones has numerous sensors. So near field communication for understanding the communication area, and proximity sensors, magnetometers, accelerometers, humidity sensor, gyroscope, moisture sensor, microphone for input of signals, fingerprint sensor, for digital barometric pressure sensor, thermometer, touchscreen, light sensors for tracking GPS, camera. So like this, various sensors are available even in our smartphone, which has made a great impact in the IoT. And for example, if we take the smart homes, where we are using hundreds of sensors, with potentially hundreds of sensors, smart homes. Similarly, if you take the example of intelligent vehicles with 100 plus sensors, wherein we are able to connect variety of cities with the thousands of connected sensors, and the list continues. The sensor industry keeps on growing, has grown to a very big extent. We can see from the figure here. So this figure shows an explosive year-over-year increase over the past several years, from bold precisions for sensor numbers in the upcoming years. See, it has gone, for example, in 2012 if you to 17, if you compare 21 to 56%, and it keeps on growing, just like the Moore's law, as we have studied in electronic circuits, the number of components in a microelectronic circuit keeps on increasing. So like this, sensors are also keeping on increasing. The size is decreasing. The power capabilities and the sensing capabilities, data capture, communication, these sensors are able to establish with the actuators. All these are possible with the recent sensors. So next type of component, what we will see in the Internet of Things is the actuators. So actuators are natural complements to the sensor. Sensor is capable of sensing some elements and store it as a digital reading. And sensors are designed to sense, measure practically any measurable variable in the physical world. Actuators receive some control signals, commonly an electric signal or a digital command that triggers some physical activity like motion, force, etc. And some action should take place. So this is one simple figure which shows the figure which demonstrates the symmetry and complementary nature of these two types of devices. The sensors where we sense and measure the values, okay, and actuators which act and which converts it into useful work, okay. So the actuators, from the digital representation of electrical signals, we are able to convert it into real world physical environment where we are able to make or derive some useful work or do some action with the values whatever we have stored in these sensors. So actuators measure the physical. One second. To better understand the actuators, just we can understand a comparison of the sensor and actuator functionality with human beings. Okay. So as we have the 5 senses, so the sensor variety of sensors, as I told, we are able to sense variety of elements and we are able to process. In our human brain, we are processing these 5 senses. But here, if we take all these components or Internet of Things or any smart devices, we have a certain processing unit embedded, and we convert it into external actions or some motions. So with the signals, whatever is generated with the help of the CPU, now we actuate these signals and convert it into real world physical actions. So as our hands and legs are used for motion, so these actuators derive some motion with the help of some processing with the sensed data, whatever is stored digitally. So actuators vary greatly in function, size, design, and the common ways to classify include the type of the motion based on the power, or whether it is binary or continuous based on the area of application or the type of energy. Based on the type of motion, actuators can be classified based on the type of motion they produce. For example, it can be linear or rotary, or in axis, single dimension, 2-dimension or 3-dimensional axis motion. Similarly, power, it can be high power or low power or micro power. Similarly, we can have binary or continuous signals. So actuators can be classified based on the number of stable state outputs, okay. So whether it is continuous or binary. Similarly, based on the area of application, actuators can be classified based on the specific industry or vertical where actually they are being used. And based on the type of energy, what energy is used for converting into action. So we have got, so these are some of the variety of actuators. Mechanical actuators, for example, we are able to understand from the lever, screw jack or a hand crank. Electrical actuators, for example, we can understand from the thyristor or bipolar, transistor or a diode. Electromechanical actuators from the motion, maybe with the AC or a DC motor or a stepper motor. Similarly, electromagnetic actuators with the help of example we can take as electromagnetic or linear solenoid. Hydraulic or pneumatic actuators, smart material actuators, or micro or nano actuators. So the microstatic motors, micro valve, comb drive. So all these are some of the actuators based on the energy type. Now we will see about the micro electromechanical systems, MEMS. So one of the most interesting advances in the sensor and actuator technology is the MEMS, we can call it as in short as the micro machines, where we can integrate and combine electrical and mechanical elements such as sensors and actuators on a very smaller millimeter or even less in scale. So one of the keys to this technology is a microfabrication technique that is similar to what we use in our microelectronic integrated circuits. And with these MEMS, we are able to do mass production at very less cost. For example, one practical example where we can understand one practical example of MEMS application is a micro pump, what we use in a inkjet printer. And for example, if we take our smartphones, we use MEMS technology like accelerometers and gyroscopes. Even if we take automobiles, the airbag accelerometers, so that uses MEMS technology. And this micro electromechanical systems, and this torsional ratcheting actuator that was developed by Sandia National Laboratory as a low voltage alternative to micro engine. So this MEMS is only a few hundred micrometers across. A scanning electron microscope is needed to show the level of detail of this figure. So microscale sensors and actuators are immensely embeddable in everyday objects. Let us understand what do we mean by smart objects. When an object can be smart, what are actual see, smart objects are the building blocks of IoT. When our things have to be smart, that means these things should be capable of sensing, actuating, and doing some actions, and we have to ensure that the processing, controlling, communication, everything is done. So if a soil sensor is connected as a part of intelligent work, actuators have to trigger irrigation systems. Similarly, if you take the same irrigation system, we can use highly interconnected sensors or actuator setup for coordinating fertilization, pest control, or even communication with the backend to calculate the crop yield, etc. So smart object, as I told, the term smart object is often used interchangeably with terms say smart sensor or a smart device or IoT device or an intelligent device or a thing or a smart thing, intelligent node, intelligent thing, ubiquitous thing, or intelligent product. So a thing which is capable of doing processing, which is capable of communicating, which possesses sensing and actuating capabilities with a power source. So then only we can call it as a smart object. So as I told, the processing should be there. So in the smart objects, processing unit for acquiring data, processing and analyzing the sensing information received by the sensors. Then we have to understand that processing unit is capable of coordinating the control signals to any actuators and controlling variety of functions with the smart objects, including communication and power. So these are in a small form, it's capable of being so flexible. It has got programming simplicity, ubiquitous, and it is having low power consumption and is of low cost. Then, as I told, the sensors and actuators, smart object is capable of interfacing with the physical world through sensors and actuators. Sensor learns and measures from environment, whereas actuator is able to produce a small change in the physical world. Whenever their changes are derived with the help of this data which is captured digitally, then only we can say that the actuator is functioning actually properly. The smart object does not need to contain both sensors and actuators, or in fact, a smart object can contain one or multiple sensors and or actuators depending on the application. And next one is the communication. So the communication within the device, which can be wired or wireless, and how actually the communication takes place. That numerous communication protocols and have been developed for variety of smart objects which are currently available. So that's the importance of the communication device in the smart objects. Similarly, the power. Okay, so as we know, So the smart objects minimized power consumption should be very, very less. And reliability. So everything is relied based on the battery power. Okay, so storage of more power in the battery in terms of improving the power efficiency, management of power, and using sleep modes, ultra power consumption hardware, and critical design elements for power. These are some of the important things in power source for a smart object. So this is one example of a smart object where we have shown one tiny low cost computer which includes a CPU, memory, a power source, a sensor, a actuator, and some communication device. So the sensor is capable of measuring the temperature, vibration, or pollution, for example. The actuator is able to perform any task like changing the traffic light signals or rotating a mirror, example, or for communication, where you're able to receive instructions and send or route data or self-organizing into networks. And power source may be solar or wind powered or battery or with AC power. So these are the recent trends in smart objects. As we know, the size has started decreasing, the power consumption has started decreasing, processing power has started increasing, communication capabilities have started increasing, and the standardization in communication is keeping on increasing. So as we know, with the influence of MEMS, so the size has started decreasing. So it has come even to the nano level nowadays. And some subjects, some of the objects we are not able to see even with our naked eye. And the reduced market sizes, smart objects are easier to embed in everyday objects. So, and the power consumption, as I told, we are able to work on the power management of these devices, wherein we are able to ensure that more power capabilities have been built in the batteries, where even some batteries are having powered sensors which can last even for more than 100 years without battery replacement. That is the recent technology where it goes with the power consumption. Similarly, the processing power is gaining increase and processors are keeping on increasing, becoming more and more powerful and miniature in size. And the key advancement for smart objects as they become increasingly complex are connected. Communication capabilities are improving. So wireless technologies are keeping on improving, and protocols, then security for the protocols, and standardization of these protocols in diverse use cases in multiple environments for multiple applications. There is a standard increase in all these technologies. Let it be power, processing, or communication. And as I told, communication is being increasingly standardized. There is a strong push in the industry to develop open standards for IoT communication protocols. In addition, there are more and more open source efforts to advance IoT. Next, we will understand about the sensor networks. So a sensor or actuator network, we call it as the SANET. Sensor actuator network is a network of sensors that sense and measure their environment and are actuators that act on their environment. The sensors and our actuators in the SANET are capable of communicating and cooperating in a productive manner. So effective. So what is that actually we expect in the sensor networks are well coordinated communication with the cooperation is the prominent challenge, where the sensors and actuators in a SANET are diverse, heterogeneous, and resource constrained. So SANETs offer highly constrained or coordinated sensing and actuation capabilities. For example, smart homes are a type of SANET that display this coordination between the distributed sensors and actuators. We know the motions and we know the values what we read and how actually things are taking place, for example, in a smart home. And similarly, the HVAC, the heating, ventilation, and air conditioning systems. Okay, for example, a smart home which can handle temperature sensors and strategically networking with heating and ventilation and air conditioning. The HVAC actuators for heating or ventilation or air condition requirements. So sensor detects a specified temperature that can trigger an actuator to take action and heat or cool home as required. So it can understand the environment and it can do on its own today. Some of the advantages of the sensor networks are the greater deployment flexibility, then simpler scaling to large number of nodes, lower implementation cost, easier long-term maintenance, and effortless introduction of new sensor or actuator nodes, better equipped to handle dynamic or rapid topology changes. Some of the disadvantages, as we know, okay, when things become wireless, then security becomes very less. For example, hijacking the access protocols and typically lower transmission speeds, what prevails in these wireless communication, and greater levels of impact are influenced by the environment. Because of the environmental conditions, loss of data can also happen. So wireless sensor networks, as we know, wireless sensors are made up of wirelessly connected smart objects, which are referred to as modes. And these wireless sensor networks, we are mainly concentrating on the limited processing power, limited memory, lossy communication, limited transmission speeds, and limited power. So this one example of a design constraint for a wireless smart object. So here, for example, if you take the processor, so the idea is to minimize the energy use, and similarly, if you take the memory, so embedding the OS, for example, using a tiny OS, or lossy communication, low power wireless mesh communication using IEEE 802.1.15.4 standard, or power line communication IEEE P1902.1, or a narrowband media for communication, maximum at 250 kilobytes per second. And this is one example of a wireless sensor network where we use for data aggregation in a variety of nodes, and we can arrive at the average temperature in all these nodes by aggregating. So this data aggregation techniques is useful for reducing the amount of overall traffic and energy in WSNs, and with very large numbers of deployed smart objects. So this data aggregation at the network edges, where fog and mist computing are critical for IoT artificial elements needed to deliver the scale and performance required by IoT in many use cases. And communication in these sensor networks can be of two types, maybe event-driven or periodic. So event-driven means transmission of sensory information is triggered only when a smart object detects a particular event or a predetermined threshold. Based on the threshold, whatever we expect, so we drive the event and we are able to detect based on the events whatever is set. Similarly, periodic transmissions for sensory information occurs only at a periodic intervals. And connecting smart objects communication criteria, if we take the various technologies used for communicating sensors can differ greatly depending on the criteria used to analyze them, based on the range, the frequency bands, power consumption, topology, constrained devices, or the constrained node networks. If we take, for example, in the communication criteria in the smart objects, if we take range, short range is there. Similarly, for example, if we take the short range alternative serial cable, example, short range wireless technologies, as we know, IEEE 802.15.1 Bluetooth and 802.15.7 visual light communications VLC is a recent trend. Similarly, medium range less than 1 mile. So maximum distance is generally less than 1 mile between two devices, which uses radio frequency signals for transmission. Similarly, at the medium range, some of the medium range wireless technologies include 802.11 Wi-Fi and 802.15.4 and 1.15.4G W personal area networks. Similarly, wired technologies which use IEEE 802.3 Ethernet and IEEE 1901.2. That is the narrowband power line communications, PLC communications. are classified as medium range. So these are the medium range communications: IEEE 802.11 Wi-Fi, 802.15.4 and 802.15.4G WPAN. And long range communication, where the distance is greater than 1 mile between the two devices, which require long range technologies. Some examples are the cellular 2G, 3G, and 4G. Recently, 5G and 6G are also research is going on in 6G. 5G is implemented. And some of the applications of outdoor IEEE 802.11 Wi-Fi and low power wide area network technologies. And these are the communication criteria where we can categorize as short range, medium range, and long range. So, right from a Bluetooth, Zigbee, 802.15.4, GRE, and 1901.2 for PLC. Similarly, for Wi-Fi, we have and similarly for 2G, 3G, 4G, and 5G. And research is going on even in the 6G platform also. These frequency bands, radio spectrum is regulated by countries and organizations using the ITU standards and the Federal Communication Commission standard, FCC standards. So these groups define the regulations and transmission requirements for various frequency bands. And some spectrum are reserved for military and for example radio, television, and it is available only for limited applications. For IoT access, the most commonly well-known ISM bands are 2.4 gigahertz band used by IEEE 802.11 BGN and Wi-Fi, and IEEE 802.15.1 Bluetooth and 802.15.4 WPAN, wireless personal area network. So these are the three main well-known or most common ISM bands. Sub bands which include IEEE 802.1.4 G, H, and low power wide area technologies such as LoRa and Sigfox. So these are the LoRa and Sigfox recently. And the frequency bands disadvantages. So disadvantages of sub gigahertz frequency band is the lower rate of data delivery, and which is as compared to the higher frequencies. And most IoT sensors do not need to send data at high rates. So therefore, lower transmission speeds of sub gigahertz technologies are usually not a concern for IoT sensor deployments. The most well-known ranges are censored on 169 megahertz or 433 megahertz or 868 megahertz and 915 megahertz. Most IoT access technologies tend to focus on 2 sub-gigahertz frequency regions around 868 megahertz and 915 megahertz. So these main bands are commonly found throughout the world and are applicable to nearly all the countries. And the European Conference on Postal Communications, CEPT, and let us take the topology, connecting the smart objects. Among the access technologies available for connecting IoT devices, 3 main topology schemes are dominant. That the one is the star, next one is the mesh, and the third one is the peer-to-peer topology, which is predominant. So star, mesh, and peer-to-peer topology for connecting smart objects. For indoor, for example, if you take an indoor Wi-Fi deployment, we prefer mostly the star topology around their access points. Meanwhile, for outdoor Wi-Fi, we may use mesh topology for the backbone of APs and the nodes connecting to the APs in a star topology. Similarly, 802.15.4 and 15.4G and even wired 1901.2 a PLC are generally deployed for mesh topology. So these are the constrained devices, and how we, according to the RFC 7228 constrained nodes can be broken down into various classes: class 0, class 1, class 2. So class 1, so this class of nodes are severely constrained with less than 10 KB of memory and less than 100 KB of flash processing and storage capability. And they don't have the resources required to directly implement an IP stack and associated security mechanisms. Example, if we take the class 0 node, is a push button that sends 1 byte of information when changing its status. This class is particularly well suited to leveraging new licensed LPWA wireless technology. Similarly, if we take the constraint node for class 2, so greater than class 0, the processing and code specific characteristics, approximately 10 KB RAM and approximately 100 KB flash for class 1, are still lower than the expected to complete the IP stack implementation. These nodes can implement optimized stack specifically designed for the constrained application protocol COAP. And this class 1 nodes to this allows class 1 nodes to engage in meaningful conversations with the network without help of gateway and supports necessary security functions. Similarly, class 2, if we take, class 2 nodes are characterized by running full implementation of the IP stack on embedded devices. So, and they contain more than 50 KB of memory and 250 KB of flash compared to class 1. And they are fully integrated in IP networks. A smart power meter is an example of a class 2 node. So these are the classes of constraint nodes, class 0, 1, 2, defined by RFC 7228. While several IoT technologies such as Wi-Fi and cellular are applicable to laptops, smartphones, and some IoT devices, some IoT technologies are more suited to specifically connect constraint nodes. So typical examples are 802.15.4, 15.4G RF, and 1901.2 APLC, LPWA, and 802.11 AH access technologies. So constraint nodes are often referred to as the low power and lossy nodes, LLNs. These lossy networks indicates that the network performance may suffer from interference and variability due to harsh radio environments. We'll take the IoT access technologies, most important topics. The topics that are addressed for the IoT access technologies, we will understand the standardization and alliances, the standard bodies that maintain the protocols for the technology, physical layer, MAC layer, topology, security, and the competitive technologies available for these various IoT technologies. First case, we will take IoT technology, the IEEE 802.15.4 is a wireless access technology for low cost and low data transfer rate devices that are low powered on batteries. Okay, this access technology enables easy installation using a compact protocol stack while remaining both simple and flexible. So this is a simple wireless protocol. Similarly, the standards and alliances, IEEE 802.15.4 or the IEEE 802.15 task group 4 defines low data rate physical and MAC layer specifications for wireless personal area networks. And since 2003, IEEE has published several iterations of IEEE 802.15.4 specification, each labeled with the publication year. For example, 802.15.4 2003 was published in 2003. Similarly, 2006 up to 2011, we have 2006, 11, 15 respectively. The protocol stacks utilizing IEEE 802.1.4 are ZigBee, 6 LoRaWAN, and ZigBee IP. Then ISA 100.11a, wireless and thread. First case, we will take the ZigBee. So IoT access technology 802.15.4 is ZigBee. So this based on the idea of ZigBee style networks in the early 1990s. So the first ZigBee specification was ratified in 2004. Later on, with the release of IEEE 802.1.4 in the previous 2003. So industry supports has grown for more than 400 companies that are members of the ZigBee Alliance. And applications used for ZigBee are some for home automation. ZigBee can be used for control lighting, thermostats, security functions. Smart energy brings a variety of interoperable products such as smart meters, monitors, and controls can be used for delivery of utilities such as electricity, water. And ZigBee products are controlled by the utility provider and can coordinate between homes and business and the utility provider itself to provide more efficient operations. So the ZigBee utilizes IEEE 802.15.4 standard at the lower physical and MAC layers, and we'll actually go to the protocol stack. So the high level ZigBee protocol stack, so 802.15.4, which includes the physical and MAC layer. Then the network and security layer, application layer, which is included in the ZigBee platform stack. And similarly, the applications or profiles in the ZigBee, which is all vendor specific for applications. ZigBee IP, with the introduction of ZigBee IP, the support of IEEE 802.15.4 continues, but the IP and TCP/UDP protocols and various other open standards are now supported at the network and transport layers for this ZigBee. So it was created to embrace the open standards coming from IETF's work on LLNs such as IPv6 or 6LoWPAN and RPL. ZigBee IP is a critical part of the Smart Energy Profile 2.0 specification from the ZigBee Alliance. SE 2.0 is aimed at smart metering and residential energy management systems. ZigBee IP was designed specifically for SE 2.0, but it is not limited in this use case. And this is the ZigBee IP protocol stack with the physical layer 802.15.4 2006 standard and MAC 802 MAC standard in 2006. And we have the 6LoWPAN adaptation layer. Similarly, IPv6, then ICM PV6 and 6LoWPAN, ND, RPL, UDP, TCP, and the Smart Energy 2.0 profile for the ZigBee IP. And ZigBee IP supports 6LoWPAN and adaptation layer. The 6LoWPAN mesh addressing header is not required as ZigBee IP utilizes the mesh over root over method for forwarding packets. So at the network layer, all ZigBee IP nodes support IPv6, ICM PV6 and 6LoWPAN, neighbor discovery, and utilize RPL for routing of packets across the mesh network. If we take the physical layer, the 802.15.4 standard supports an extensive number of physical options and range from 2.4 gigahertz to sub-gigahertz frequencies in ISM bands. The original IEEE 802 released in 2003 standard specified only 3 physical options based on the direct sequence spread spectrum, DSSS modulation. So the DSSS modulation technique in which a signal is intentionally spread in the frequency domain, resulting in greater bandwidth. We take the physical layer. The original physical layer transmission options were as follows: 2.4 gigahertz, 16 channels with a data rate of 250 kilobytes per second. Similarly, 915 megahertz with 10 channels with data rate 40 kilobytes per second. 868 megahertz with only one channel with a data rate of 20 kbps are only a 2.4 gigahertz band which operates worldwide. And this physical layer, if we take, as I told, IEEE 802.15.4 2006, similarly 2011, 2000 introduced additional physical communication options, physical layer communication options, including OQPSK PHY. The DSSS PHY employs the offset quadrature phase shift keying, that is OQPSK PSK modulation. Similarly, this OQPSK is a modulation technique that uses 4 unique bit values that are signaled by phase changes. An offset function that is present during phase shifts allow the data to be transmitted more reliably. Now, if we take the physical layer, the BPSK modulation, and the next one is the ASK amplitude shift keying, BPSK modulation. So this is a parallel sequence spread spectrum, PSSS in physical layer. So PSSS is an advanced encoding scheme which offers increasing range throughput data rates, signal integrity compared to DSSS. ASK amplitude shift keying uses amplitude shifts instead of phase shifts to signal different bit values. So this is one example of a physical layer format, IEEE 802.15.4 physical layer format. So 6 bytes for the preamble, that is synchronization header, physical header, frame length, which includes the frame length, and 0 to 127 bytes for the physical service data unit, PSDU. The physical layer, the synchronization header for this frame is composed of the preamble and the start of the frame delimiter fields. So the preamble field is a 32-bit 4-byte parallel construction pattern that identifies the start of the frame and is used to synchronize the data transmission. The start of frame delimiter fields informs the receiver that the frame contents start immediately after this byte. If we take the physical layer header portion of the physical layer frame shown in the figure, it is simply a frame length value where it lets to know the receiver that the total amount of data to expect in the physical services PSDU portion of the 802.4.15 physical layer. The PSDU is a data field or the payload. MAC layer, if we take for example the IEEE 802.15.4 MAC layer, manages access to the physical channel by defining how devices in the same area will share frequencies. So these are some of the tasks performed in the MAC layer in 802.15.4, network beaconing of the devices which act as coordinators, how devices can beacon to join the network, the PAN association, disassociation by devices, the device security, reliable link communication between two peer MAC entities. And the MAC layer achieves these tasks using the MAC frames which are specified in 802.15.4. The data frame handles all the data transfer of handles all transfers of data. Similarly, the beacon frame is used in the transmission of beacons from the PAN coordinator. Acknowledgement frame confirms the successful reception of the frame. MAC command frame is responsible for control communication between the devices. So this is one example of IEEE 802.1.4 MAC format. So this MAC frame, the frame control has 2 bytes, similarly sequence number with 1 byte, and 4 to 20 bytes are reserved for the addressing fields, which includes the destination PAN identifier, destination address, the source PAN identifier, and the source address. And the frame payload is a variable, that is the actual MAC payload, and 2 bytes for the frame check sequence, that's a MAC footer. So the actual physical frame, 6 bytes reserved for the preamble, as we have seen earlier. We notice that the MAC frame is carried out as the physical payload. So this MAC frame can be broken down into MAC header, MAC payload and the MAC footer fields. MAC header, MAC payload and MAC footer frames as shown in the figure. So this MAC layer header field is composed of the frame control, sequence number and the addressing fields. MAC control fields define the attributes of frame type, addressing modes and other control flags. Similarly, the sequence number field indicates the sequence identifier, and the addressing field specifies the source and destination of the PAN identifier, where we are able to identify the source and destination address fields. At the MAC layer, the MAC payload field varies in the individual frame type. For example, the beacon frames have specific fields and payloads related to the beacons, while MAC command frames have different fields present. MAC footer field is nothing but more than the frame check sequence. We call it as the FCS. So FCS is nothing but a calculation based on the data in the frame that is used by receiving side to confirm the integrity of the data in the frame. Then the topology, if we take IEEE 802.1.14 based networks, can be built as star, peer-to-peer or mesh topologies. We'll see some other technologies. If we take next security aspects of the IEEE 802.15.4 security, IEEE 802.15.4 specification uses advanced encryption standards, AES with 128-bit key length for the base encryption algorithm for securing data. AES, as we know, is a block cipher, which means it operates on fixed block sizes of the data. And in addition to the encrypting of the data, AES validates the data that is sent, and this is accomplished by a message integrity code, MIC, which is calculated for the entire frame, and enabling the security features for 802.1.4 changes the frame format slightly and consumes more payload. Using the security enabled field, the frame control portion of the header is the first step to enabling AES encryption. And the auxiliary security header is created at the source address field, stealing some bytes for the payload field. So this is one example which shows a frame format with the auxiliary security header field for 802.1.4 2006 standard and later versions, where we have 2 bytes for frame control, 1 byte for sequence number, the addressing fields, which includes 4 to 20 bytes, 4 to 20 bytes, which includes the destination PAN identifier, destination address, source PAN identifier, and the source address, and auxiliary header, security header, that is 14 bytes, 0 to 14 bytes, and we have variable frame payload and 2 bytes reserved for the frame check sequence. So the MAC header, MAC payload, and MAC footer are the major components for the security. Security enabled bit in frame 1 control is set to 1. Auxiliary security header field is added to MAC frame. And other competitive technologies, IEEE 802.1. Physical and MAC layers are the foundations for several networking profiles that compete against each other in the various IoT environments. And the competitive radio technology is different in its physical and MAC layers in -7. -7 was originally based on ISO 18001 standard and positioned for industrial communications, whereas IEEE 802.1.4 is more generic. So we will see some of the important points in IEEE 802.1.4. So wireless, physical and MAC layers are mature specifications that are the foundation for various industry standards and products. Physical layer offers maximum speed up to 250 kbps and is robust, and it handles association and dissociation of devices from PAN, reliable communication between devices, security, and formation of various topologies. And as I told, it includes star, peer-to-peer, or clusters, trees that allow for formation of mesh networks. From security perspective, 802.1.15.4 utilizes AES encryption standards and has edge in the marketplace through all the different vendors and organizations utilize this physical and MAC layers for building various applications. IoT sensor deployments require low power, low data rate, and low complexity. We will see the other technologies, IEEE 802.15.4G and 4E. So which is more suitable for environmental wireless sensors in smart cities, electrical vehicle charging stations for smart parking meters, microgrids, and renewable energy. So this 802.15.4G and 4E. So the standardization and alliances because of this 802.15.4G 2012 and amendments made the same group 4 standards. We maintain the standards and integrates them into the next release of the core specification. The additional capabilities and options available in 4G12 and 4E12 led to additional difficulty in achieving the interoperability between devices and mixed vendors that users have requested. So the profiles are based on open standards such as 4G12, 4E12, IPv6, 6LoWPAN, and UDP for the FAN profile. Physical layer. Okay. Let us take the IEEE 802, 4G and 4E. Physical layer, 4G 2012 standard originally had a maximum PSDU or payload size of 127 bytes, which was increased for the Sun PHY to 2047 bytes. So this provides a better match for the greater packet sizes found in many upper layer protocols. For example, the IPv6 MTU setting in is 1280 bytes. Fragmentation is no longer necessary at the layer 2 when IPv6 packets are transmitted over IEEE 802.15.4G MAC frames. The error protection was improved, evolving the CRC from 16 to 32 bits. We take the physical layer, the data rate in bands ranges from 169 megahertz to 2.4 gigahertz. So these bands are covered in the unlicensed ISM frequency spectrum specified by various countries and regions. Within these bands, data must be modulated onto frequency using at least one of the following physical mechanisms to be 4G compliant. And the physical layer, the multi-rate, multi-regional frequency shift keying, MR, FSK, then the MR OFDM, orthogonal frequency division multiplication, then the MR OQPSK, as I told earlier, the multi-regional offset quadrature phase shift keying. So these are some of the features in the MAC layer. While IEEE 802 4E12 standard amendment is not applicable to the physical layer, it is pertinent to the MAC layer. So this amendment enhances the MAC layer through various functions which may be selectively enabled based on various implementations of the standard. Then the MAC layer, the following time slots. So we call it as the time slotted channel hopping. Time slotted channel hopping, TSCH. The TSCH is an 802.1.15.4E 2012 standard MAC operation mode that works to guarantee media access to the channel diversity. Channel hopping is also known as the frequency hopping. Utilizes different channels for transmission at different times. TSCH divides time into fixed time periods or time slots which offer guaranteed bandwidth and predictable latency. So where the number of time slots are defined as time slot frames, and where we are able to guarantee access, the transmitter receivers agree on the channels for the timing and switching between channels, and combination of the global time slot counter and global channel hopping sequence list as computed in each node to determine the channel of each time slot. So as the TSCH is robust and suitable for noisy environments and smoother coexistence with other wireless technology, especially for industrial use cases. Similarly, the MAC layer information elements include the information IEs. We have a specified tag length TLV format, which allows frames to carry additional metadata and support MAC layer services. And these services may include 9 key management. Then we have the enhanced beacons, EBs. EBs extend the flexibility of IEEE 802.15.4 beacons to allow the construction of application specific beacon contents. Similarly, at the MAC layer, we have the enhanced beacon request EBRs, where we are able to leverage IE, selectively specify the request for examples. And for example, a device can query a PAN that is allowing new devices to join, or a PAN that supports a certain set of MAC or physical capabilities. Then enhanced acknowledgement, integrating the frame counter and the frame being acknowledged, and the feature helps to protect against certain attacks that occur when acknowledgement frames are being spoofed. So this one example of the IEEE 802.15 GRE MAC frame format. The talk security, as we see the security, inherit the security attributes from this 2006 standard 0.1.5 802.15.4 2006 specification. Encryption is provided by AES standard 128-bit key. In addition, there is an auxiliary security header field initially defined in the 2006 standard, a secure acknowledgement and secure enhanced beacon field complete with the MAC security. And this is the example of the IEEE 802.154 GRE MAC security layer. So the security header is composed of auxiliary security field and more information field elements, and the competitive technologies G and E are parallel with technologies which compete with 802.154 such as -7, and 802.1.4.15.4 is well established and already deployed in many scenarios, mostly outdoors. So next, one more technology is the IEEE 1901.2 narrowband power line connection. So it's a narrowband spectrum for low power, long range, and resistant to interference, which carries over the same wires that carry electric power. And this 1901.2A is used for smart metering, for automated reading of utility meters such as electric, gas, water meters, smart energy solutions. We are able to get all these things through the PLCs. Similarly, the distribution automation, NB PLC includes monitoring and controlling aspects. Then NB PLC is often used in this public lighting, electric vehicle charging stations. NB PLCs for electric vehicle charging station, where the batteries of electrical vehicles are charged. Then NB PLCs are used for these microgrids, local energy grids that can disconnect from the traditional grid and operate independently. Renewable energy such as solar, wind power, electric, or the geothermal heat energy. Then the standards physical layer frequency band operates from 3 to 500 kilohertz, and working group standards 1901.2 has integrated support for worldwide regions in order to develop worldwide standards. Then this organization is responsible for standardizing the electrical engineering for unique in Europe especially. And the CENELEC A and B bands refer to 9 to 95 kilohertz and 95 to 125 kilohertz respectively. The physical layer FCC, the Federal Communication, that is a US government organization, regulates the interstate intercommunications by radio, television, wire, satellite, and the cable. FCC low band encompasses 37.5 to 117.1875 kilohertz, and the FCC above Senelec band is 154.6875 to 487.5 kilohertz. So, and these are the frequency bands, as I told, the physical layer, the MAC layer. So, for running out of time, I am unable to discuss more things on these 1901.2 A standards. And IoT technologies, this topology, this one example of a figure, it shows a network scenario in which a PLC mesh is applied to a neighborhood scenario, which uses the IPv6 mesh in a NB PLC scenario. Security, similar securities just like 15.4G. Encryption and authentication is performed using the AES standards. In addition, aligns with 802.154G and its ability to support key management protocol. Similarly, security. Hello. Hello. The over, sir. Just 2 minutes. Last technology we will see about the LoRaWAN. Recent technology, it is a few set of wireless technology known as the low power wide area technology, or the long range and battery powered endpoints are available. LPWA technologies, battery powered endpoints. So for want of time, I feel I have to conclude. So we will take only one topic, that is the IoT access technology, LoRaWAN security. Okay. So each endpoint implements a network session key used by the LoRaWAN network server. The network key security ensures data integrity, computing and checking, encryption and decryption of the MAC only data message payloads, and the application session key encryption description functions and the endpoints in the application servers. And so with this, I would like to conclude my session. Thank you very much. I thank the organizers for giving me the opportunity to share a session on the smart objects, the things in Internet of Things. Since I have got more slides, I am unable to share within the limited 1 hour of time. Thank you. I thank the HoD of ISE, Dr. Rajendra, for providing me this opportunity to deliver a session on the smart objects, the things in Internet of Things. Thank you, sir. Thank you very much.
Thank you for the informative session, sir. Sir, we have few questions from the participants.
Yes, madam.
The first question is, what are the applications of IoT in medical field?
Applications in medical field. Recently, we are experiencing, even in this, actually in the COVID-19 season. So what actually we expect? So we expect so many, for example, the pressure, for example, we are using infrared thermometer for checking the temperature, then for checking the oxygen levels, for checking the blood pressure, even glucose, everywhere. So these are some of the industrial applications where in medicine, where biosensors are used more critically to check the sugar, temperature, pressure, and ECG levels. So all these medical devices are recently using these microcontrollers and applications. Yes, madam.
Okay, sir. The next question is, for POC of IoT projects, whether we can use standard sensors or ordinary sensors which is available in the market.
Now, what is it? POC means? What is that, madam? First question once again.
POC stands for proof of concept, sir.
Proof of okay.
For
For proof
POC of IoT projects, whether
Ah.
we can use standard sensors or ordinary sensors.
The standard sensors are commonly available in the market. I feel we can use the standard sensors and we can get better results instead of using ordinary sensors. Because we have to establish a proof of concept means we can use the standardized sensors itself.
Okay, sir. The next question is WSN and IoT?
We can imagine we are computing and sensing. Yeah. Yes, madam.
Okay, sir. Next question is,
one is an application.
What about smart digital sensors?
Smart digital sensors. All the devices, whichever is available, as we know, the technology has evolved so much, where we have built internet in everything. So this IoT and all has changed this concept. It has become internet of everything also. And everywhere we need to use internet, and not only specific things. We want to use in everything. Most of the things, in everything we want internet. So I think that our question is answered.
Thank you, sir. The last question is, how IoT can be used in energy harvesting of cluster head in sensors?
Energy harvesting.
Energy harvesting of
energy harvesting means, once again, we have to go to the power consumption. We have to talk about the battery power consumption, how we can save energy, how we can preserve energy, and what method technologies we can use for saving energy, putting the nodes into sleep mode. Only these areas we have to focus to harvest energy in the wireless sensor networks or all these smart objects or devices.
Thank you, sir. Thank you
ma'am.
for your valuable time. We look forward for further collaboration with you, sir. Thank you again.
Thank you, ma'am. Thank you.
I thank all the participants for being part of today's session. Tomorrow, we will be having a session on IP as the IoT network layer by Dr. Nagappa U. Bajantri, HoD CSE, Government Engineering College, Chamrajanagara at 3 p.m. So meet you all tomorrow. Thank you.
Thank you, ma'am.
Thank you, sir.